Hi, everyone. Today is another edition on our sequence on measurement statistics, quantum non-locality, quantum contextuality, and the topological approach to these things. Getting right into it, the XOR measurement. So we want to consider a situation where we have just the simplest possible situation. Alice and Bob have one input each, and then they formulate a little table like this, as we've discussed before. How can we think of this XOR measurement? Think of Alice and Bob and some third party Charlie. And what happens is when Alice gets one of her outcomes, call it A, which could be 0 or 1, and Bob gets one of his outcomes, B, which could be also 0 or 1, all Charlie does is add those two numbers together, forget what A and B was, and just remember what their sum is, modulo 2. By modulo 2, I mean that multiples of 2 even numbers are going to be given by 0, and odd numbers will be given 1. So what we have is that Charlie, the probability that Charlie gets an outcome 0 will be the sum of the probabilities for Charlie to see the outcome 0. So that happens when Alice and Bob send him outcomes 0, 0, and when Alice and Bob send him outcomes 1 and 1. So to get that probability, you sum these two numbers along the diagonal. To get the outcome 1, you have to sum these two probabilities, for example. Now, we want to actually sort of encode this topologically. So we have this normal representation of Alice, Bob, and Charlie like this, where we have the marginals given in red, blue, and purple. Now, we can actually sort of do something a little bit interesting, and we're going to see the benefit of this later on, is that instead of just this square table, we're going to encode this into a triangle. So what are we doing here? We take each measurement, so a measurement input X for Alice is assigned to one edge of this triangle. A measurement input Y for Bob is another edge. And Charlie's measurement, the so-called XOR, is a third edge. And the probability that Alice gets 0 are the sum of these two numbers. Probability that Bob gets 0 is the sum of these two numbers. Probability that Charlie gets 0 is the sum of these three numbers. And so we have this nice little geometric shape that we can see. Each of the marginals just is coming from this 0, 0 at the middle, and you sum to find the appropriate marginal. You sum 0, 0 with the number that's closest to that edge. So if I want to find the 0, 0 marginal for this one, I sum these two numbers, so on and so forth. So I want to talk about simplices. So this triangle is an example of a simplex, and simplices is the plural of that. So zero-dimensional simplex is a point, a one-dimensional simplex is a line, a two-dimensional simplex is a triangle, and a three-dimensional simplex is a tetrahedron, and then you can keep going on in higher dimensions. The way that you define these in higher dimensions is that a higher dimensional simplex or generalized triangle always has one of its edges, or sorry, one of its vertices is neighboring. So I can take one vertex and it goes along an edge to each of the other neighbors. So this vertex is a neighbor to this one, and this one. And I can do that for all of them. This one is a neighbor to all the others as well. So that's how you define these for higher dimensions. And in general, the way that this works is we want to think of each of these triangles are going to be related to some sort of like measuring apparatus, some measuring scenario. And every time that you have two triangles or two generalized triangles that are touching, then you're going to have some sort of compatibility relationships. But before we get into that, actually, just the way that we construct these spaces in the theory of simplicial sets or using simplicial complexes, that you have some generalized triangle, a simplex, and the way you construct straight spaces is by gluing or attaching another triangle along one of its faces. So I can take this triangle here and glue it along an edge of this tetrahedron. But what I can't do is take this triangle and glue it just any old place geometrically. I can't do that. It has to only be along one of these lower dimensional faces. So I can glue this triangle to to a line along the vertices, and then so on and so forth. So there's many different things you can do. The only thing you can't do is just ad hocly glue things arbitrarily. They have to be along the lower dimensional faces. And when I say face, the face of a tetrahedron, it has many faces. So it has two-dimensional faces, which are these four triangles on the boundary of this tetrahedron, but it also has lower dimensional faces than that, which are the six edges of the tetrahedron. And then also lower than that are the vertices, the zero-dimensional simplices, of which there are four, for example. We're actually going to focus for our purposes, and this is a sufficiently rich enough set of examples, two-dimensional spaces. By two-dimensional, I don't mean that it might be the case that you need to sort of, to visualize it, we need three ambient dimensions. That's possible. But what I mean are two-dimensional surfaces. All we ever use are triangles, lines, and points. There are no tetrahedrons arising in our example sets. And this will be okay. We'll get a bunch of really nice examples just from this. So how does this work? So we have, for example, that we could do before Alice has one measurement, Bob has two measurements, and then non-signaling just means that I sum up these two numbers and these two numbers. I can do the same exact thing with triangles. So now at the intersection of these two triangles is the measurement x. And so now the numbers that sum up in these red circles over here, those will just be given by these sums. Remember, you take the middle one, and sum it with the one that's closest to the edge that you want. We could do the same thing for Bob. Bob has one measurement, Alice has two. And then this time you just glue along the y edge instead of the x edge. And of course, in each of these, you have these XORs. Now, what's nice about these triangles is that it affords more flexibility for how to glue things. For example, I can glue along this XOR edge just like this. And I can easily represent this with a picture like the one that I have here. I have x0, y0, x1, y1, and they have to have the same XOR, just like this. So that means that these two numbers sum to these two numbers. Okay, very nice, very simple. We're just taking things and meshing them together. And whenever we do that, we sum the two numbers that are adjacent to that edge. But of course, we can't easily represent this sort of situation just using the boxes. Now, let's see, for example, we have this CHSH scenario. What does this look like in this picture? So before we had, for the CHSH, we had this 2x2, or rather 4x4 table with 16 entries. It's going to turn out to be the case that there's at least, and perhaps there's more, 3 different ways of representing this same scenario. And the fact that there is many different realizations of this scenario topologically, this is another sort of advantage to some extent for representing these things. So how does this work? Let me start with the simplest example. For each of these cells, 1, 2, 3, 4 up here, we have one triangle, 1, 2, 3, and 4. Now, for each triangle, so I didn't write down all the numbers and all of the measurements here, but say this is so this could be one of the measurements x0, and what we have here is that this number and this number must add up to this number and this number. So I drew a little circle, and then this one will be one of Bob's measurements because it can only be an x and a y in each triangle. This will be another one of Alice's. This will be another one of Bob's. And what we see is that when we sum up the numbers, we sort of have this nice looking pattern where things link up into a circle. In fact, this scenario, and it's much more evident in this topological picture, these are called cycle scenarios. CHSH is an example of a cycle scenario. It's a lot easier to see when you represent it topologically. Now, This particular picture happens to topologically be a disk. So just something like this. Not geometrically, but topologically. Another instance could be something like a cylinder. So what do I have here? I have I have 1, 2, 3, 4 triangles. Each time I have a triangle along one of the edges, I sum up the numbers for Alice. I sum up the numbers for Bob, Alice, Bob, so on and so forth. Interestingly enough, you also see again that you have this sort of linked pattern. And you're going to say, well, this is not a circle. The reason that this is a cylinder is because I am identifying this edge with this edge. So I just take a sheet of paper, like so, and then along the two endpoints of a strip of paper, I glue them. And so that's a cylinder. So this CHSH scenario can also be looked at as a cylinder. Or it can even be something weirder than that. Here I have a punctured torus. So a torus is just a donut. And the way that you represent that topologic, so just with a sheet of paper, first is take a square sheet of paper, you glue these two edges, and then once you glue those two edges into a cylinder, you take the other two edges and then you curl them around and then glue those together, then you have this donut. So I'm saying that these two edges are the same, these two edges on the top and bottom are the same, and the reason it's punctured is because I have nothing here. Somebody took a bite out of this donut. As you can see right here. And so also you have again that you have this sort of circular linked pattern going on here, because I have these two numbers equal these two numbers, these two numbers equal these two numbers, these two numbers equal these two numbers equal these two, and so you have this linked sort of pattern. So just to sort of recap and maybe give ourselves some ways to start thinking about these on our own. For example, let's look at a couple of interesting exercises. What are the spaces for these scenarios? So I will give you a hint for this one first. We already looked at a similar situation, which is this one. When I have these two linked together, I have two triangles glued along a common edge. Now I have three boxes. How do I do that third box? Now for this one, I have a CHSH scenario, but with Bob having one extra measurement. What does this look like? My recommendation, take a look at this scenario and just think about how you can add one more measurement for Bob here and what the space looks like after that. Another thing that you might want to think about is, and this is sort of exemplifying the sort of flexibility of simplicial sets and this sort of topological picture, is say I have a triangle like this, and what I do is I glue two edges of the same triangle. So I just take two of the edges and I glue it together. So now I have a topological cone like this. And I ask, what are the non-signaling conditions for this space? Okay, this is an interesting question. I think you guys can, at home, can just think about this very quickly, and you'll see that it's not so hard to figure out what's going on. Okay, thanks for listening. See you next time.